Okay, let's talk about combustion. So, when we are burning any fuel in air, so the reaction is fuel plus air would give carbon dioxide and water. And usually, when we are talking fuel, it's a hydrocarbon, meaning it's made of carbon and hydrogen, and air is oxygen and nitrogen, primarily speaking. So, if we write air, we know it is 21% of oxygen and 79% nitrogen. Usually it's 1% argon along with 78% nitrogen. But we could say it's 79% nitrogen. So if we take the ratio of N2 over O2, so if we take that ratio of nitrogen over oxygen, that's 0.79 divided by 0.21, which is about 3.76. So we could write that air is oxygen plus 3.76 times nitrogen. Okay, so now if we talk of stoichiometric combustion, so what does that mean? Well, stoichiometric combustion means it's complete combustion. So that's, as I said, complete combustion. With exactly enough fuel. Oops. Complete combustion with exactly enough fuel and air. And when you have the appropriate amount of air for the fuel that you have, the byproducts are CO2 and water. So these are the only two byproducts in that case, CO2 and water. And these are the only products. Now, if we talk of incomplete combustion, so that's non-stoichiometric or incomplete combustion. For incomplete combustion, we have fuel is not completely or fully burned. And the fuel is not completely burned, or you can say oxidized. So there's incomplete oxidation, and these will also form VOCs, um, primarily carbon monoxide, actually carbon monoxide, other unburned hydrocarbons, NO, and other pollutants. So that's when we have incomplete combustion. Okay, so now let's look at an example. This is, I think, example 2 in your sheet. So here you have to write a balanced reaction for the stoichiometric combustion of gasoline, which is represented as C7H13, including nitrogen in air. And then what are the concentrations of the products in the exhaust gas? So if we solve this, so C7H13 plus, let's say, in air, right? And air we just said is oxygen plus 3.76 nitrogen. And if it is stoichiometric combustion, we will get CO2 and water, and also because we are considering nitrogen in air, so there will be nitrogen as well. So if we try to balance this equation, so let's just assume X moles of air, and there's Y moles of CO2, and there's Z moles of H2O, and the nitrogen actually is pretty straightforward, would be, as you can see, 3.76 times X. So now we have to kind of solve for these X, Y, Z. So if we do the carbon balance, so first usually we balance the carbon, so always, so Y is equal to 7, pretty straightforward. If we do the hydrogen balance, so here we can see there are 13 on this side, so 13 is equal to 2 times Z, so which implies that Z is equal to 6.5. And now if we do oxygen balance, so 2x on the left hand side should be equal to 2y plus z. We already solved for y and z, so x would be equal to 2 times y is 14 plus 6.5 divided by 2 is equal to 10.25. And so now we could actually replace the equation. Let's rewrite the equation now. So you see C7H13 plus, so X is 10.25 moles of oxygen, plus, if we multiply 10.25 times 3.76, that will give us 38.54 moles of nitrogen. and which produces 7 moles of CO2 plus 6.5 moles of water and 38.54 moles of N2. So we just rewrote the equations with these X, Y, and Z that we just solved for. Okay, so now we will be doing the second part of this problem, which is the second part says what are the concentrations of the products in the exhaust gas. So, and the volumetric concentrations. So, the volumetric concentration that we have learned, YCO2 would be, okay, so just, I think we know this, but let me just write this again. That moles is proportional to volume, right? Why? Because PV is equal to nRT, so moles and volumes are proportional to each other at a given temperature and pressure. And so we could just look at the moles and calculate the volumetric concentrations. And the total moles of exhaust gas is, if I add up all these, so 7 plus 6.5 plus 38.54, which gives 52.04 moles. And I'm going to call this as N sub T or NT. And now let's calculate, say, the concentration of CO2. That would be NCO2 divided by NT, which is 7 divided by 52.04, which is equal to 0.1345 or 13.5%. And if we do YH2O or Y water, that's the moles of water divided by the total moles, so 6.5 divided by 52.04, so this is about 12.5%. And last but not the least, actually here you'll see the YN2 would be moles of N2 divided by total moles is 38.54 divided by 52.04, which is equal to 74%. And so these are our three these are our volumetric concentrations, and these are assuming water remains, assuming that the water remains as vapor and does not condense. The water remains as vapor and does not condense. Because if the water does condense, then of course the calculations will change accordingly. Okay. Another concept I want to introduce now, it's kind of actually a pretty important concept. It's air to fuel ratio. So air to fuel ratio is an important concept in combustion, especially vehicular combustion, because the amount of pollutants that are formed are a function usually of how much air do you have and how much fuel do you have. So that ratio becomes pretty important. So air to fuel ratio is you have mass of air divided by the mass of fuel, and it's usually in terms of mass, but when talking of vehicles, sometimes you can also be in moles. You could also be dealing in moles. So when talking of vehicles, could also be in moles. So, and then we will be using the molecular weights to convert from moles to grams. Okay, so now let's look at another example. And so the example is, what is the air to fuel ratio for the stoichiometric combustion of gasoline? So that's actually, I think, example 3 on your sheet. So I don't know why this says 1 here. Okay, let's solve this. So we just actually solved in the previous problem the stoichiometric combustion of gasoline. So I'll just want to rewrite that equation. So C7H13, 10.25 moles of oxygen plus 38.54 moles of nitrogen, 7 moles of carbon dioxide plus 6.5 moles of water plus 38.54 moles of nitrogen. So in this example, the air to fuel ratio would be air to fuel, we can call it also A to F. So air, so this is, on the left hand side, this is air, and this is fuel. So that's 10.25 moles of oxygen, or let's do one thing, let's try to color code it a little bit. And 10.25 moles of oxygen, and oxygen is 32 grams per mole. Plus 38.54 moles of nitrogen, and we have 28 grams per mole of nitrogen. And then we divide, let's draw this a little bit straighter, and that's fuel. We have 1 mole of C7H13, and this would be, actually, if you calculate the molecular weight, 97 grams per mole. So if we do the math on this, this would be equal to 10.25 times 32 plus 38.54 times 28 divided by 97. So the A to F is 14.5. So that actually you would see later on is a pretty important number. 14.5 air to fuel ratio on a mass basis for stoichiometric combustion of gasoline. Okay. The next concept is equivalence ratio. So equivalence ratio is given by phi. So equivalence ratio, it's another important parameter denoted by phi, is given by A by F stoichiometric divided by A by F ratio actual. So it's a ratio of ratios. So the air to fuel ratio stoichiometrically divided by the air to fuel ratio for a given situation. And if you just mathematically invert the things, so you could say this is F by A ratio actual divided by F by A stoichiometric. And an inverse of phi is lambda. So sometimes phi is used and sometimes lambda is used, but lambda is 1 over phi. Now phi less than 1, the equivalence ratio less than 1 means this is fuel lean, and phi greater than 1 means it's fuel rich. And you can kind of deduce that if you see that F by A actual divided by F by A stoichiometric, then if this is greater than 1, so you could kind of try to understand how that might be the case. If it has more fuel than air, then the actual would be higher than the stoichiometric, and then that's why it's fuel rich. And so fuel lean means you have excess air and less fuel, and because you have excess air, so the exhaust contains oxygen because not all the air was used. And for the fuel rich, it has not enough air and in this case you won't get proper combustion and you'll form pollutants. And also, just to say the lambda is greater than 1 in this case. Let's see, the lambda is greater than 1 and the lambda is less than 1, just because lambda is, inversely proportional to the equivalence ratio. So in combustion equation, if we are working with the combustion equation, we find the amount of air, and find the actual amount of air, so we can use this ratio to find the actual amount of air being used. So say it's burning gasoline, and that's our typical equation, right? And then we have some products, and so we have phi or phi. Some people say it as phi, some people say that as phi, but I'm just saying it as phi here, is F over A actual divided by F over A stoichiometric, or as we said, A over F stoichiometric A over F actual, and then if it's, it's 1 mole of fuel in each case, so the F cancels out, and it is equal to A stoichiometric divided by A actual so this is X stoichiometric divided by X actual. So if you want to find X actual, usually that's what we are looking for. So X actual is X stoichiometric divided by phi, the equivalence ratio phi. Okay, let's do an example. I think this is an example 4 in your sheet. So what is the air to fuel ratio if gasoline is burned at an equivalence ratio of 0.8? And write the complete equation for this reaction. So we are given a phi value of 0.8. And let's see. So, okay, if that's what's given, and we need to find the air to fuel ratio, right? What is the air to fuel ratio in this case. Right, so let's write down the definition of phi. That's air to fuel ratio stoichiometric divided by air to fuel ratio actual. And stoichiometric, from the example we did earlier, 14.5 divided by air to fuel ratio actual. So if we solve for this, would be 14.5 divided by 5, which is 0.8, which is equal to 18.1. So that is pretty straightforward. And okay, if see, if you want to confirm this, so when phi is 1, that means the moles of air are 10.25, and when phi is 0.8, the moles of air would be, say, 10.25 divided by 0.8 is 12.81. So we say C7H13, 10.25 moles of air. Usually we have that, right? And but now we have, like, this is not as we said, the moles of air are divided by phi, and then just in this case, which is 0.8, so 7CO2 plus 6.5 water, but then we don't know how much oxygen, or actually how much nitrogen is there, and so this is an unknown. There'll be nitrogen, and there'll be oxygen, because it's, because we just discussed the phi value is less than 1, so it's a fuel lean condition, and the exhaust air will contain some amount of oxygen. So, but we don't know how much. But we can relatively easily calculate. So let's see, C7H13. So we just substituted from here. So we can write here 12.81 times oxygen plus 3.76 times N2 plus N2 can be directly calculated, 48.17 N2 plus, so if I call this, let's say, W moles of oxygen. So we can do a quick balance on O. So 12.81 times 2 on the left hand side of this reaction is equal to 14 plus 6.5 plus 2W. So if we solve this, we get W is equal to 2.56, and so I can replace this right here back in the equation. 2.56 O2, and that actually is the second part of the problem. What is the balanced equation for this reaction? And then we can check, actually we can check the A over F. So 12.81 moles of oxygen, 32 grams per mole for oxygen, plus 48.17 moles of N2, and we have 28 grams per mole for nitrogen, divided by 1 mole of C7H13, 97 grams per mole. And if we calculate this, we get A by F is equal to 18.1, which we had also calculated previously right here. So that means it all fits well together. So there's just confirming that what we did, everything did not have any errors. Okay, so the next thing we're going to look at a little bit is the temperature effect. So how do these emissions change with temperature? Or how do these parameters change with temperature? So if I draw this plot of equivalence ratio, the phi value, and temperature on the y-axis in, say, Kelvin, and an equivalence ratio is 1 is considered stoichiometric. Then you could have less than 1 and say more than 1, and so let's draw a dotted line right here in the center, because I'm drawing a dotted line here because below this is the fuel lean region, and on the other side is the fuel rich region. And if we say this is about 2000 Kelvin, right here, so the plot actually looks something like this, and it's more qualitative in one sense. something like this. And so there's like it increases and then reduces. And why does that happen? So there is, as you can clearly see, there's a peak near equivalence ratio equal to 1. And the reason is, when it's fuel lean, then it has to heat excess air. So when it has to heat excess air, in this region, it cannot heat it to that temperature, to that higher degree temperature. And when it's fuel rich, at that point there's too much fuel and you're not fully burning the fuel. So here you're not fully burning the fuel. And for that reason also, for that reason as well, the temperature is lower than what it's at, the equivalence ratio of 1. So, and then if we want to look at, okay, let's draw another plot. So the same 0, 1, 2, and we are plotting phi on the x-axis, but now on the y-axis if we plot the volumetric concentration of the pollutants. So again, this is, the left hand side is phi less than 1, this is phi greater than 1, this is excess air, and this is not enough air. And if we draw different pollutants, so actually the NO, the nitrogen oxide, is very much related to the temperature. So as we saw that wait a second, trying to draw it more accurately, the trend. So something like of this sort. There's a peak at 1 for, this is for NO, and then a couple of things that I would like to plot are the hydrocarbons, and they look something like this. And then carbon monoxide, which looks, let's see which color do I want to use. Carbon monoxide. So when there is excess air, there's actually complete combustion occurring. So pretty much carbon monoxide is 0 till that point, but then it starts to take off. So it's 0 till a phi value of 1. I'm showing it, it seems, okay, let me correct that slightly. So it's actually like completely 0, not close to 0. And so this is, on the x-axis we have phi, but if we have the air to fuel ratio, that would look a bit different. So at the equivalence ratio, it's 14.5 at the stoichiometric conditions, and then this would be, just again more qualitative numbers than anything else. So a high phi value means it's fuel rich, and if it's fuel rich, then A2F is lower. And if we draw now this one on the A2F plot, 10, 15, 20, and so because near 20 is our equivalence ratio equal to 1, and now if we do the same plots, they will just be a mirror image. And the hydrocarbon and CO would look the opposite as well. So that's the hydrocarbon plot, and then the CO plot is like this. Let me try to do that again. Oops. Okay, let's see. So so this is carbon monoxide, and this is NO. Okay, based on what we have learned so far, let's try to fill in this table. It provides a summary of all the concepts that we have been looking at in this lecture. So we have, we have to fill in these options in this table. So less than or equal to or greater than 14.5. So for fuel lean conditions, and these are with respect to the fuel. For stoichiometric, we know it's 14.5. When it's fuel rich, there's more fuel, so this will be less than 14.5, and this will be greater than 14.5. And equivalence ratio, if phi or phi is greater than 1, then it's fuel rich. When it's less than 1, it's fuel lean, and when it's stoichiometric, it's equal to 1. And for lambda, it's the opposite, so we can sort of just do it the inverse of whatever we are doing in the other one. Now, what about the power generated in terms of fuel lean, stoichiometric, and fuel rich? Well, for fuel lean, you have less fuel and more air, so the burning is not proper, so this one is usually the poor or the least of the three, so this will be poor. And fuel rich, when you have lots of fuel, and actually the power generated is highest in that case, and this is average. So this is high, and this is average. And but the fuel economy in case of fuel rich, because you're wasting a lot of fuel, it's not getting burned properly. So this is the worst fuel economy. And here, when the power is poor, you're working, you're driving your motor on a, or your engine on least amount of fuel. So this is actually the best average or the best fuel economy. And this one is the average. Now carbon monoxide, when your fuel lean, then it's low, and it's low even when it's stoichiometric, but then it's high in this case when it's rich, fuel rich. And hydrocarbon, they kind of show the same trend, when it's fuel lean, then you can say the hydrocarbon is actually low. So this would be low, medium, high. And for NOx or nitrogen oxides, as you've seen, this will be low, high, and low. So there's some things to keep in mind, and just want to reiterate them a little bit. Carbon monoxide, it is a result of incomplete combustion. And when we have fuel rich, that means phi is greater than 1. There is not enough oxygen, and then you produce carbon monoxide. And then when there are also, you produce CO when there is poor mixing of fuel and air. So when there's poor mixing of fuel and air, there are pockets, there are regions which are fuel rich. So you have fuel rich regions in the flame. So, in fact, if you were to write that kind of an equation, it would be C7H13 plus oxygen, but as I said, we have not enough oxygen, and we have some N2, and now usually if it's complete combustion we would form CO2 and 7 moles of CO2, but this time it will be less than 7. I don't know, I'm not putting a number here because that will depend. And in addition there will be some CO that will be formed, some carbon monoxide, and then of course we have water, and some N2. Okay, with that we'll stop and see you in the next lecture.